All right, so we're starting Unit 4, Momentum, and this includes Chapter 6, Momentum in your textbook. And we're going to be covering the topics of momentum, impulse, how impulse changes momentum, conservation of momentum, and kind of talking about the idea of collisions, and just introduce the idea of some more complicated collisions than a 1D collision, but we will focus most of our problem solving on just one-dimensional collisions. This unit builds upon forces, especially with Newton's first law and Newton's third law. So Newton's first law was the law of inertia, which meant that things in motion tended to stay in motion unless acted upon by an outside force. And then Newton's third law, which was that forces come in pairs. So when two objects interact, there's going to be equal but opposite forces on those two objects. So momentum is a property of a moving object. Okay, so it's basically inertia in motion. So momentum, that's exactly what it means. It means inertia in motion. So it's going to be the mass of an object, its inertia, multiplied by its velocity. We're going to use a lowercase p with an arrow to represent momentum. M is mass, and then velocity is, represented by v. Some examples of different momentum. So you could have a moving bus going down the highway and a car going down the highway at the same speed, but the bus will have more momentum because it has more mass, as it has a different mass than the car. Another example could be if you have two cars, one going down the highway doing 60 miles an hour, the other going 30 miles an hour. Well, the car going 60 will have more momentum than the car only going 30. A car that would be stopped at rest would have no momentum because it has no velocity. So a moving object does it have momentum, does it have energy, does it have speed, or does it have all of these? The correct answer is all of these. All right, so up until now, we've really only talked about speed or velocity, and now we're introducing momentum, but we're going to get into energy in the next chapter. And actually, energy is important to understand certain types of collisions later in this chapter, but just as the idea of, what is energy, not so much how do we solve with energy. Here's another quick check-in. So when the speed of an object is doubled, its momentum remains unchanged in accordance with the conservation of momentum, doubles, quadruples, or decreases. And the correct answer is it doubles, because as we can see, P is equal to mv. So if v goes up by a factor of 2, the momentum would have to go up by a factor of 2. So this brings us into the idea of impulse. And what impulse is kind of looking back to kind of Newton's almost second law, which is the idea that a force can change the acceleration of an object. So if I took a force and I put it on a mass, it's going to accelerate that object. Well, if that acceleration occurs for a certain amount of time, it's going to change the velocity of that object, which is kind of what the idea of impulse is. So it's a force acting on an object for a certain amount of time. So we can represent impulse with this capital letter J. The reason we don't use I is used later on when we get to electricity. So we've used J. So force times a change in time will be impulse. But that impulse, because it's going to change the velocity or change the momentum, can be written that it's a change in P, or a change in momentum, or m delta v, because it's not like it's changing the mass, it's really changing the velocity. So kind of an example of this is a force that's applied over a short interval of time will produce a smaller change in momentum than the same force applied over a longer interval of time. So it's like tapping on the gas in your car versus holding the gas down. So you're changing the force, it's just you get that short burst, that short change in velocity, versus if you hold the gas down, you get a longer change, longer time with the force, which gives you a larger change in velocity. So here's another quick check-in. So when the force that produces an impulse acts for twice as much time, the impulse is not changed, doubled, quadrupled, or halved. Okay, so the answer is it's doubled, right? So if we define J as F delta t, so again, if time goes up by a factor of 2, the impulse will go up by a factor of 2. So as we said before, impulse can change momentum. So J delta P. Okay. So kind of some applications of this get into things like golf. So when you're playing golf or even baseball, when you swing a club or you swing a bat, you want to follow through. You don't want to just kind of stop abruptly when you make contact with the ball. And that's because you're trying to increase the time of contact. By increasing the time of contact, you create a larger impulse or a larger change in momentum, which means the ball gets to a greater velocity. Because the goal in golf or the goal in baseball is to get that ball to go as far as possible. Kind of similar with this, we get into the idea of if I change the force instead for the impulse. So when you hit a nail with a hammer, all right, so we have kind of different masses here with the same impulse. So when you hit a nail with a hammer, you have a very small force with a small hammer, but a larger hammer will give it a much larger force over the same time interval. So you get a different impulse. So whether you're using what we call a finish hammer versus like a sledgehammer, you'll get a different amount of force there driving the nail in. So another quick check-in. So a cannonball shot from a cannon with a long barrel will emerge with a greater speed because the cannonball receives a greater what? Average force, impulse, both of these, or none of the above? The correct answer is impulse. So we know that J is equal to F delta T. So we can think of that, the delta P, the change in momentum, is F delta T. So the F really kind of is fixed, right? There's only so much force that that explosion can create. But by staying in the barrel longer, we get a larger time interval that that force is acting on. So we get a larger kind of impulse or larger change in momentum that could occur. So now, some other important examples with this. So if you get a car out of control, it's generally better to try to collide it with something soft. So if you've ever watched IndyCar, on the corners on an IndyCar race, they always make either piles of hay bales or piles of old used tires. And that's because you don't want a vehicle that's going really, really fast to stop in a short interval, like hitting a brick wall. You want it to have a chance to slow down over time. So by giving it something that's going to cause that impulse to happen over a larger interval of time, that change in momentum to happen over a larger interval of time, it decreases the forces involved. So larger T, smaller F. We actually engineer this now into cars. When we think of crumple zones in cars, the whole point of the crumple zone in the car is to make the car stop in a larger interval of time. Instead of just all of a sudden solid car, like, think like built like a Matchbox car or a Hot Wheels car that doesn't crunch or doesn't crush. That's bad because then all the forces are transferred into you. You stop in a shorter interval of time. Car looks better, but overall you get more damage to you internally, organs, brain, whatever it is, as opposed to if you let the car crunch up and, do its thing, you actually might lose the car, but you survive the crash. So in this case, it's the impulse equaling the force change in time, okay? And the impulse also equaling mass times change in velocity tells us that the force change in time is equal to the mass change in velocity. So another quick little check-in here. So a fast-moving car hits the haystack or hits a cement wall, and they're going to produce that vastly different results. So do they both experience the same change in momentum? Do they both experience the same impulse? Do they both experience the same force? So are all three of those statements correct? Are only 1 and 2 correct? Are none of them correct? Or are 1 and 2 not correct? So 1 and 2 are correct. So they're going to experience the same change in momentum because the vehicle is going from one speed to another speed. So delta V is the same. It's the same mass. So that's the same change in momentum. And change in momentum is impulse. The force, however, is different because one has a larger time with a smaller force, one has a smaller time with a bigger force. So you either have little f, big T, or you have big F, little t. Just depends whether you stop short or you stop over a longer period of time. So now, when a dish falls, will the change in momentum be less if it lands on a carpet than if it lands on a hard floor? No, both are the same. Yes, it's less if it lands on the carpet. No, it's less if it lands on the hard floor. Or no, it's more if it lands on the hard floor. The answer is no, they're both the same because it starts at some initial velocity when it gets to the floor, and it has to go from that initial velocity to 0. So it's the same change in velocity, right? So for us, delta V is the same for both, and it has some mass. So it's the same delta P. What's different, though, is it's equal to F delta T. So on the carpet, delta T is larger, so the force is smaller. Whereas on the hardwood floor, the delta T is the smaller amount, so it gives you a larger force. So, kind of one of our final real-world examples with this impulse changing momentum gets into kind of the physical realm, jumping or boxing or some physical activity. So in jumping or kind of sports like parkour, it's really critical that you bend your knees when you land. Because you can jump from very high heights and land safely as long as you bend your knees to increase your contact time with the ground while slowing down. Because it lessens the force on your body during impact. So if you've ever watched anybody do parkour in like YouTube videos or in real life in Boston, when they jump, they kind of go from fully rigid straight to crouch down by the time they actually stop their body. And that gives their body time to slow down, so that the forces in the body are very, very small. Another thing like this goes into boxing. In boxing, they always say the term roll with the punches. And that's because they're trying to, again, increase that contact time with the punch. The punch has the same change in momentum that has to occur. Okay? So the same m delta v has to occur. But by increasing the delta t, they reduce the force on, the face. Whereas if they just try to hold their ground and stay in place, it's going to hurt a lot more because the force increases as delta t decreases. So that brings us into conservation of momentum. So this is now when we start looking at two objects at the same time. So the law of conservation of momentum basically states that in the absence of any external forces, so like no friction, no extra forces that are going to slow things down unnaturally or like springs or things like that, the momentum of a system is going to remain unchanged. So that if before some sort of collision or explosion happens, there's a certain amount of momentum between two objects, after they interact, we're going to have the same amount of momentum. It's just, it might change which object that momentum's in. So, for example, the force on the cannonball inside the cannon barrel is equal to and opposite the force on the cannonball in the cannon. That's Newton's third law, right? So we saw the cannonball went to the right, the cannon goes to the left in terms of the forces. So what happens is the cannonball gains momentum while the cannon itself gains an equal amount of momentum but in the opposite direction. So we're used to, again, dealing with the idea of the force on the cannon from the ball is equal to but opposite the force on the ball from the cannon. All right? But one of the things we just talked about with impulse is that impulse is related to F delta t. So if I think of impulse over time as just force, it starts to make sense that really an impulse over time is what's occurring with a force. So since the explosion happens for the same amount of time for both, I can think of it like this. I can say that, well, if this was FCB for a certain amount of time, it'll be equal to but opposite FBC for the same amount of time, right? Well, mathematically, putting delta t on both sides is just like multiplying by 1, okay? But the other way to think of this is it's delta p. So the delta p on the cannon from the ball is equal to but opposite the delta p from the ball on the cannon, okay? So you start to understand why they have to have the same change in momentum, all right? But what's different for both is, well, one is the mass of the cannon, the change in velocity for the cannon. One is the mass of the ball, the change in velocity for the ball. So we start to understand, well, the cannon's got more mass, so it's going to have a smaller change in velocity. The ball has less mass, so it's going to have a larger change in velocity. All right? And this is all just based around Newton's third law. So we can actually expand this out a bit more. So again, looking at this idea of the total momentum before a collision happens, and we'll talk about this in terms of object A and object B instead of, cannons and balls. So object A, object B is like saying the momentum before a collision in object A plus the momentum in object B before the collision has to equal the same momentum in A and B afterwards. But what happens is it just changes what object it's in. So if before the collision, all the momentum was in one object, after the collision it could be shared between both. Or if there was some momentum in A and some momentum in B, after the collision they kind of share it a bit. So think of it almost like bank accounts in some ways. So imagine you had $100, but it was split up between like $20 in one account and $80 in the other. They collide, and then all of a sudden you've got $70 in one account and $30 in the other. That's what this idea is of conservation of momentum. It's just like we're swapping where the momentum is, what object it's in. There's two different kind of nomenclatures you might see. The most common one is the kind of first one here. I'm going to put a little star next to, which is the MAVA, which means the mass of object A, the velocity of object A, plus the mass of object B, velocity of object B. And they're referring to this point to the initials for velocity, is equal to MAVA prime, and the prime means like the final state, plus MBVB prime, the final state. I'd like to show you that because that's what, when you get to college, will probably show up in a textbook somewhere because they like to use this prime notation. The version I like to do, and I'm going to put a nice little green check mark here, I like to be implicit about saying, hey, it's the initial state, hey, it's the final state, by using an I and an F next to those A's. I know it's a little extra bit of writing, but it helps you in your mind keep track of this is A's initial velocity, this is B's initial velocity, this is A's final velocity, this is B's final velocity. Again, it just helps that extra step. And all we're doing here is basically keeping track of the initial momentum and the final momentum. Okay, that's what it is. So it's saying all the initial momentum equals all the final momentum. And we'll do problem solving this as we go through the unit. So this brings us to collisions. And there's really two, and I'll call it 2.5 types of collisions we have, because there's a special case for one of the types of collisions here. So we have inelastic collisions, and this is what most of the collisions we're going to deal with are. And these are collisions that occur when two objects, hit each other. There could be some deformation that occurs, and some heat could be generated. Energy is either lost or gained. So this is, two objects hit, they go crunchy, crunchy like a car crash, Or this could be like an explosion. So there's something that's there, and then all of a sudden something goes boom, some energy is added. One piece goes one way, one piece goes the other way. And it's called an inelastic collision. There's a special case of this. So this is why it says like that extra half. And with a completely inelastic collision, what occurs is the objects stick together either in the initial state or the final state. Normally it's the final state. So imagine a car crash where two things come together and they stick together. Or like a train comes down the tracks and the two trains kind of couple together and stay together after the collision. That'll be a common problem that we'll look at as we kind of go through things. Or imagine like a train car coming down and they dump snow into it or coal into it and it stays with the car. That's another type of completely inelastic collision. And all that's special about that case, again, is that they have the same final velocity in that special case. Okay. But again, it follows that same equation. I've used the traditional equation there just to show you. So it's about the initial states versus the final states of momentum. The elastic collision gets to be a little different. So for an elastic collision, the objects collide and they're going to rebound without any deformation or generation of heat. So this is really what happens for like air molecules or things at the atomic level. So the particles come in, they hit, the momentum is conserved, so the initial momentum of the two particles equals the final momentum, but energy is also conserved. So there's some fancy equations that I'm not going to bore you with that tell us that the velocity initial for A equals the velocity final for A. So I'm going to rewrite this with the final. So VA initial plus VA final equals the velocity initial for B plus the velocity final for B. Okay? So this is just that special case for elastic that's telling us that if I add the two velocities of object A together and the two velocities of object B, that also holds true, along with conservation of momentum. So again, if we look up here at these examples on the right-hand side, in the first case, you have the black object, so this is like case 1 up here. The black object has mv initially, and the blue object has no velocity. So they collide, and they just swap momentums. So the black one comes to rest, the blue one gains all the v. All right? In case 2 here, we can look at initially the black one has positive v, the blue one has negative half of v. After the collision, again, they swap momentums. So the black one gets the negative half of v, the blue one gets the positive v after the collision. Case 3, it's kind of like collisions, you know, a car getting rear-ended. The faster one with v is the black, hits the blue, which initially has half of v, and then after the collision, it's the black now has the half of v and the blue has the v. Again, they're following this pattern of conserving momentum and that energy equation that we can derive. Again, I'm not going to bore you with that derivation, but it is something just to kind of understand that it's an extra piece that's happening. So, for collisions, here's a little checking. So we have a freight car A moving towards an identical freight car B that's at rest. When they collide, both freight cars couple together. So this is that completely inelastic case I talked about. Compare with the initial speed of freight car A, the speed of the coupled freight cars is the same, half, twice, or none of the above. So it's going to be half because it comes in with V and then it leaves with half of V. And why is that? Well, we'd be starting with MA with a V plus MB with 0. So the total there would be just MAV. Okay, that's going to have to equal my MA, this new V final, plus my MB, which has the same V final. Okay? So, they gave us this extra thing, is that they're identical freight cars. So let me give a simple thing and say that the mass just happens to be 1. So if MA is 1 and MB is 1, that would tell me that I've got 1V equals 1VF plus 1VF. So that means V is equal to 2VF. So that means that VF will be equal to 1 over 2 V, or half of V, after the collision. So just to kind of sum up on this last slide here, for more complicated collisions, we could have, because velocity is a vector, 2 dimensions that things collide in. So something could collide in the x-axis and another's moving in the y-axis, but as long as we keep track of momentum in each axis separately, so momentum in the x-axis, momentum in the y-axis, we could solve for it. And that's what happens with, like, collisions where cars come into an intersection, or coins when you flip 2 coins on a table, or something when it explodes and pieces go off in different directions. We're not going to do problem solving with complicated collisions, but it is just an interesting concept to understand.